Flight 191 plunged to the ground 4,600 feet from the end of the runway.
And this is part 2 of the crash of Flight 191. The focus of this video is going to be on the maintenance procedures. We're going to look at some maintenance documents, and we're going to define those documents. We're going to look at the NTSB and the FAA's final report. We're going to look at an animation that shows the maintenance procedures that was used. But first, we're going to look at an animation that shows what the flight crew encountered and how they followed protocol to correct what they perceived was happening. You have to remember, they can't see the left wing and they can't see the number 1 engine, so they have no idea that that engine has departed the plane. So let's go ahead and look at the video.
As American Airlines Flight 191 rolled down the runway for takeoff, the left engine and pylons separated from and went over the left wing. As the engine assembly separated, it caused damage in the area of the wing where it had been attached. The damage included rupturing in the hydraulic lines to the outboard leading edge slats in the left wing. Following the engine separation, and as the airplane climbed away from the runway, the pilot assumed that an engine had failed, and he input rudder to counteract the yaw from the resulting asymmetric thrust. The airplane seemed to climb away normally and accelerated to 171 knots. Just after liftoff, the leading edge slats on the left wing, no longer locked in an extended position by hydraulic pressure, began to retract. Also at this time, as American Airlines procedures called for a climb at V2, the pilot flying began a slow deceleration toward V2. The depiction of the aerodynamic lift curve represents the area on the curve and the resultant lift, or CL, and angle of attack when flying at V2. Note that the scheduled V2 was well below the angle of attack where wing stall occurs. In normal 1G flight, a deceleration or reduction in airspeed would result in an increase of lift, or CL increases, and a corresponding increase in the angle of attack until the wing stalls. The slats and flaps are extended for takeoff and landing to in part allow lower stall speeds, and thereby allow lower flight speeds and shorter takeoff or landing distances. On Flight 191, when the outboard wing slats retracted, the wing was reconfigured such that the effective stall speed for the wing was increased. On the lift curve, this means that the wing stalls at a lower CL and angle of attack. This was significant for Flight 191 in that the increased stall speed was now above the scheduled V2. The lift required by the wing to fly at V2 was greater than the lift it was capable of generating with the slats retracted. The result was a left wing stall at a speed above V2 and a loss of control. Under normal circumstances, the wings, being identically and symmetrically configured, each generate roughly half the lift required by the airplane. The lift generated offsets the airplane weight, and during a climb, the generated lift is greater than the weight of the airplane. When the slats retracted on the left wing, it then became incapable of generating the same lift increment as the properly configured right wing. This lift asymmetry resulted in a roll to the left that was initially countered by an aileron input. Not shown here are roll spoilers that also would have extended on the right wing to increase the roll power. The pilot would have made roll control inputs to raise the left wing back to level. The aileron deflections shown here are consistent with that intent. Finally, as the airplane was decelerated to the stall speed for the left wing, the roll caused by the lift asymmetry overpowered the control authority of the airplane, and an uncontrollable left roll resulted.
First, let's look at what some of these documents that I'm talking about that we may or may not look into and see what they actually mean. So one of the first ones we have here is an advisory circular. So the advisory circular, or the AC system, provides a single uniform agency-wide system that the Federal Aviation Administration uses to deliver advisory material to the FAA, customers, industry, the aviation community, and the public. So it's just a way of giving some information out. Now, a supplemental type certificate is another document that they use, and it's a a type certificate that is issued when an applicant, such as an airline or a manufacturer, has received FAA approval to modify an aeronautical product from its original design. The STC, which incorporates by reference the related TC, approves not only the modification, but also how the modification affects the original design. So now they're changing something and so they need a STC approval. The next two that we want to look at are the service bulletins and the aircraft owners. So manufacturers issue aircraft service bulletins to inform owners and operators about critical and useful information on aircraft safety, maintenance, or product improvement. Compliance with service bulletins may or may not be mandatory, but you should never ignore them when it comes to safety. In this instance, McDonnell Douglas issued a service bulletin that was the reason this repair was done. The next thing is an airworthiness directive, and it's under FAA authority. So airworthiness directives are legally enforceable rules issued by the FAA in accordance with 14 CFR Part 39 to correct an unsafe condition in a product. 14 CFR Part 39 defines a product as an aircraft engine, propeller, or appliance. So this, you may not have to do it, but you should pay attention to it. This AD, it is a directive. You must do this. So the next thing and the last thing we're going to look at as far as these type of documents is the engineering change order. So an engineering change order, or ECO, outlines new product designs or proposed changes to existing designs and listed all affected parts and assemblies. It will include the reason for the change, documentation, drawings, manufacturing disposition codes, revision details, cost information, and other relevant information. That's pretty much what we need to know here. Now, engineering change orders, in this instance, what was used is they're not changing. What they are changing is the procedure. So they don't want to follow the procedure in the maintenance manual to remove the pylon. They came up with a new procedure, and that's what this engineering change order does in this instance. Okay, now that we've defined some documents, let's look at the NTSB's report. We're going to look at it, and then we're going to read some excerpts from it. But what you should know is it's a 104-page report, and I've just pulled out some pages, but there's still quite a lot of information that I want to look at. So first of all, 271 persons on board Flight 191 were killed, 2 persons on the ground were killed, and 2 others were injured. Can't ever forget that. So the National Transportation Safety Board determines that the probable cause of this accident was the asymmetrical stall and the ensuing roll of the aircraft because of the uncommanded retraction of the left wing outboard leading edge slats and the loss of stall warning and slat disagreement indication systems, resulting from maintenance-induced damage leading to the separation of the number 1 engine and pylon assembly at a critical point during takeoff. I'm assuming anytime there's a separation of the number 1 engine, it's going to be at a critical point. The separation resulted from damage to improper maintenance procedures, which led to failure of the pylon structure. Now, when I'm reviewing these documents, sometimes I make notes over here, and it's like my first take of my first read-through. So here I look at, I made a comment, cause and effect. They say the cause was the asymmetrical stall. I say the cause was the improper maintenance, and the effect of that was the improper stall, or the accident was by the asymmetrical stall. So let's move further down. This is a diagram of that pylon section. So this aft section here, this is the aft bearing that was actually, the service bulletin calls out to be changed. The wing clevis, this is attached to the bottom of the wing where this goes in there. This is the bulkhead area here. So this is what we're looking at. It says May 31st, 1975 and February 1st, 1971, that McDonnell Douglas issued a DC-10 service bulletin 5448 and 5459. Now we're going to go ahead and go to the service bulletin now and look at it and see what it says. So here's the service bulletin over here, 5448. This is the one we're concerned with. Attach fittings, replace engines 1 and 3, aft pylon, attach spherical bearings. So let's go down here and see just some of the important information I've highlighted here. So the first, this incorporated, they changed this compliance to recommend, and it was optional. So they recommend doing this now. It was optional. You can do it if you want, but now we recommend it. So the repetitive inspection requirements outlined in DC-10 Service Bulletin 5445 are superseded after accomplishment of this Service Bulletin. So 5435 would have you, after so many hours, look at this bearing and see what condition it was in, and then at that point you would make your determination. So you could do this Service Bulletin, but until you do this Service Bulletin, you have to do that one. Go through effectivities of the aircraft and everything like that. So let's come down here. So this is McDonnell Douglas recommending to everyone that's doing this service bulletin. Note, it is recommended that this modification be accomplished during engine removal. It's recommended, and it's to be accomplished at the operator's convenience. So it's not you have to do it now. It's when it's convenient for you to do it. And the man hours do not include time for engine removal installation. That's twice they said, basically inferred or said, remove the engine. Come down. It is recommended that operators perform this modification during engine removal. That's the third time. The following instructions assume the engines 1 and 3 are removed. So here is a drawing of the bearing itself and the bushing and the bolt that goes through there to hold the aft end of it to the wing. So, and it's also making a note here to visually inspect the bulkhead for damage and install the new bearing. So visually inspect bulkhead for evidence of damage, usually gouging or bearing into the bulkhead, and accomplish the following. So you're going to do this once it's removed from the aircraft. So you're supposed to be looking at this area once you remove it from the aircraft. That's important. Let's go back to the NTSB. It is recommended that this procedure be accomplished during engine removal. That's what the service bulletin said. However, the Vice President for Maintenance and Engineering at American Airlines testified at the Safety Board's public hearing that the manufacturer's consideration for maintenance timing is not necessarily consistent with air carrier operations. For example, American Airlines maintenance cannot forecast with any great accuracy when or where an engine would have to be changed. Since it has been scheduled, it would have been impractical to try to carry out the procedures of Service Bulletin 5448 in that manner, and the aircraft would have to be scheduled to undergo the modification. Service Bulletin 5448 directed the pylons were to be removed in accordance with the procedures contained in Chapters 54 of the DC-10 Maintenance Manual. Chapter 54 called for first removal of the engine and then removal of the pylon. So I said these are the procedures that are called out in the Service Bulletin telling you what you need to do. According to the manual, the sequence for the removal of the attached fittings was the forward upper attached assembly, the forward lower attached assembly, the thrust link, and the aft bolt and bushing. So the aft bolt and bushing were supposed to be the absolute last thing you disconnect. American Airlines decided to comply with Service Bulletin 5448 and 5459 and to perform the work during a maintenance C-check. Now, a maintenance C-check is accomplished after so many hours in service. But the C-check usually lasts from 1 week to 4 weeks, depending on the amount of maintenance that is required for that check. So whatever the work package is for that C-check determines how long that C-check is going to last. So they were doing the maintenance C-check at its Tulsa Maintenance Base facility. On July 28th, 1979, American Airlines issued Engineering Change Order R2693, establishing the maintenance procedures for accomplishing the modifications contained in the service bulletins. So right here we see that American didn't want to follow the maintenance procedure in the maintenance manual, which is an approved procedure. They wanted to come up with their own procedure. And they had learned that United Airlines had been using a crane system, a hoist system to remove the engine and pylon as assembly. So they came up with their own procedure to do the same thing, but instead of a hoist, they're using a forklift. While establishing the maintenance procedures for the 4 DC-1030s, American's maintenance and engineering personnel evaluated the feasibility of raising and lowering the engine and pylon assembly as a single unit using a forklift type supporting device. This technique would save about 200 man-hours per aircraft, but more importantly, from a safety standpoint, it would reduce the number of disconnects, hydraulic and fuel lines, electrical cables, and wiring from 79 to 27. So you're taking a procedure that they know how to do, and you're changing it to a procedure that is not common. So it's a brand new procedure. So I'm not sure how safe that is. If you're worried about safety, your mechanics probably know how to disconnect an engine and put it back together and reconnect it. American Airlines personnel contacted McDonnell Douglas personnel about this procedure. According to the American Airlines manager of production for the Boeing 747 and the DC-10 in Tulsa, who participated in the development of the maintenance procedures, a McDonnell Douglas field service representative stated that McDonnell Douglas did not know of any carrier that was removing the engine and pylon as a single unit. He said that the field service representative conveyed concern in reference to clearances to me. However, he assumed that these clearances involved those between the clevis and the fore and aft faces of the pylon bulkhead spherical bearing. So McDonnell Douglas field service representative who was contacted by American Airlines stated that he conveyed American's intentions to his superiors. According to him, Douglas would not encourage this procedure due to the element of risk involved in the remating of the combined engine and pylon assembly to the wing attach points, and that American Airlines personnel were so advised. So he's concerned about once you're putting it back together. He has no concept at this point that the damage could occur when you're taking it down. So McDonnell Douglas does not have the authority to either approve or disapprove the maintenance procedures of its customer. Just because they don't recommend it, they can't tell them not to do it. It's up to American to do what they want to do. So American Airlines decided to lower the engine pylon assembly as a single unit and requested that McDonnell Douglas provided information concerning the CG, center of gravity, of the engine and the pylon, including the nose cowl and fan cowl, both fan cowl and core cowl thrust reversers as a single unit. The single unit was to be lowered by a forklift on March 31st, 1977. McDonnell Douglas field service representative informed his company that American Airlines proposes to drop the wing engine's pylon as a single unit package directly onto an engine stand by means of a forklift, and then asked for the CG of the pylon in the above described condition. On April 8th, 1977, McDonnell Douglas furnished the data to American. Next, American Airlines used the newly developed removal method to modify the 4 foreign DC-1030s. While working on the first aircraft, the maintenance personnel had difficulty removing the forward bulkheads attach assemblies before removing the aft bearing bolt and bushing. They reversed the procedure and found that removing the aft bolt and bushing first expedited the removal of the forward attach assemblies and the thrust link. Now, remember earlier we saw that in the maintenance manual, the aft bolt and bushing were supposed to be the last thing removed, and they state here that they actually reversed it. So the reverse procedure was followed on the remaining 3 aircraft, and the modification program was completed. Those were DC-1030s. The incident that happened with 191 was a DC-1010, and the difference between the two is there is a greater distance between the flange and the clevis. So now we come with the issue of using the forklift. So they have a center of gravity that's different than what it would be if you were to take the engine off by itself. So they needed to know what the center of gravity was and where they needed to line up the forklift. So there was no mark on the forklift denoting the midpoint between the forks. Therefore, alignment was a visual estimate. We're talking a lot of weight here on a forklift. So you really want to know exactly where the center of gravity is so that you can get that correct. One mechanic said it could be limited to the operation of the forklift. So the operation of the forks on the forklift, mechanic said it could be limited to a 0.001 inch. The estimates of others range from a quarter of an inch to 0.06 inches. My note here is, how did they measure it? And we're using a lot of visual cues here. It doesn't look like they're using any measurement equipment. Also up here, as I said, they did it in reverse order, so they're using out-of-sequence work. They're not doing it per the sequence. Anytime you start varying sequences, then you could possibly run into problems. So maintenance personnel stated that the 2,000 to 3,000 pound pressure bleed off on the pressure gauge was common. However, they all stated that the lifting forks did not move. So now they've got all the weight on the forklift, and they're telling you that there is a pressure bleed off. Supervisory personnel stated it was normal for gauge reading to bleed off 2,000 to 3,000 pounds during a 15-minute period without any perceptible load movement. Well, supervisory personnel are not out there doing the job, so I don't know how they know that. The load remains fixed because of frictional load on the mast and rollers. Although mechanics testified that the load did not move, they also said that they would manipulate the controls to restore the original reading on the pressure gauge. So when you're using this type of, they're moving stuff and manipulating the forklift to make sure it stays where it's supposed to. When you need very small movements, that's not a good thing. From March 29th to 31/1979, the accident aircraft underwent the spherical bearing modification. On April 19th, 1979, the forklift's maintenance log contained a write-up which noted in part, troubleshooting forks creeping down under load. There was no record that a corrective action was taken. On May 17th, 1979, the log showed inspect lift cylinder per engineering. There was no record of any findings. On June 20th, 1979, the forklift was tested for drift down. An engine pylon assembly was placed on the lifting forks, and the forks drifted down 1 inch in 30 minutes. A lift cylinder check was found to be defective. So there were write-ups on this forklift prior to them using it on this accident aircraft. And nothing was done. They said they didn't find anything and they didn't fix anything. They used the forklift to do the repair on the aircraft. And then after the crash, they went back and took the forklift out and they tested it under the same load that it was under when they did the repair, and found that there was a bleed down of 1 inch in 30 minutes. And they had a defective check valve. So I don't want to tell you exactly what they found yet, but I will say here, the cover sheet of the ECO, which was R2693, was classified and the repairs as minor. So it classified the repairs as minor. Now, changing the bearing is minor, but I'm thinking that if you're going to have to drop an engine and a pylon off the wing to do that, you might want to classify it as a major repair. So the procedure developed by American Airlines and issued under ECO R2693 was within American Airlines authority and approval or review. No approval or review was sought nor required from the manufacturer or the FAA. So basically, there's procedures in place or a program in place where American Airlines can develop their own procedure. They don't need authority or approval from the manufacturer or the FAA. So next, let's look at an animation showing the maintenance procedure that was used to drop the engine and pylon as a unit to change the aft spherical bearing.
The damage occurred almost 2 months before the crash, when during a required repair, Flight 191's left engine pylon assembly needed to be removed. Maintenance procedures prescribed by McDonnell Douglas call for mechanics to first remove the engine from the pylon, then remove the pylon from the wing. But in an effort to save time and reduce the possibility of errors in reconnecting the various components, mechanics at Tulsa planned to remove the engine and pylon as a single unit, using a forklift to support the assembly as it was being disconnected from the wing.
Now, I'd stop the video right here because this animation states that it was the mechanic's plan to use a forklift to drop the engine and pylon as a unit. Now, this wasn't the mechanic's plan. This was the procedure that was outlined in the ECO that was developed by American Airlines. The engineering department in American Airlines are the ones that came up with this procedure, and the mechanics are just following the procedure that was outlined. So let's go back to the video.
McDonnell Douglas was aware of the procedure, but did not approve of its use.
There was a deformation that was occurring right at the very top of this, where the mating clevis, where the engine and the pylon come together, as if the clevis had impacted that area and had produced the downward motion onto the flange that caused the crack. In order for the clevis to go down and make an impact, it had to have been disassembled at the time when that impact occurred. That clevis would not normally be at that position.
So let's look at a diagram and a couple of photos. So here we have the aft bulkhead. This is where the flange is down here. You got the bolt that goes through. You got the bearing, inner race and bearing, and spherical bearing is here. So they have to take this bolt out. This is going to drop down out of this clevis, which is attached to the bottom of the wing. And you can see it over here. And you can look at it here, and you can see the distance between the bottom of this wing fitting and the flange. It's not very far. So the bottom of the bearing is here that goes across. So this is what they're going to have to take out. So all of the maintenance that they're doing to this area is right here within an inch or two. And we'll look at another document, one of the photos, and see where they have, it's hard to see the measurements, but you can see the measurements from it. So let's look at another photo. This is a photo showing, this is not that engine. This is another engine where they found the problem. So if you look at it, you see this is an inch, 2, 3, 4, 5, 6 inches. So this is a 6-inch ruler. And here's the bottom of that hole, or where the bearing is. Now this is still together, but if we're looking at this, we're seeing the bottom of this is about here. So we got 1 inch. Maybe, I mean, you're talking 1.5 inches from where the work that they're having to perform, once this is all removed, the work they're having to perform to where the damage occurred, an inch, inch and a half. And you can see from the service bulletin, it said to inspect the bulkhead and the spherical bearing and all this for damage around there. So I don't see how they could miss it if this occurred on removal. The next picture is a clearer picture of it. So you can also see this here, where once again, this is where this part contacted this, and where the crack propagated. And we're really not that far from the bottom of this bearing here to where this is. So they should be able to see that. Next, let's take a look at another animation that shows the procedure. But remember, this one is produced by the FAA. So let's look at it.
In order to reduce the time required to perform maintenance on the pylon attachment fittings of the DC-10, American Airlines developed a procedure to remove the engine and pylon as a unit. The maintenance required removal of the pylon from the wing, and procedures specified by McDonnell Douglas assumed that the engine would already be removed. The engine is supported by a pylon that is in turn attached to the wing. The expected maintenance would be to remove the engine, then remove the pylon, and complete the pylon inspections. To save time, American Airlines removed the engine and pylon as a unit, rather than separately, a deviation from procedures specified by the airplane manufacturer, McDonnell Douglas. The wing pylon attachment points are shown in this illustration. The engineering work order for removal and replacement of the wing pylon assembly required removal of the forward attachment fittings, followed by removal of the aft attachments. When difficulty was encountered removing the forward fittings, maintenance personnel reversed the sequence and removed the aft fittings first, which facilitated removal of the forward fittings. During this operation, the engine pylon assembly was supported, lowered, and raised for reinstallation using a forklift with an attached engine stand. Tight clearances in the attachment hardware required very precise manipulations of the forklift controls in order to avoid unwanted contact of the attachment surfaces. This sequence depicts the removal of the pylon attachment hardware in preparation for lowering of the engine and pylon as a single unit. The aft attachment fittings were removed, followed by the forward attachments, and the engine pylon assembly was lowered for the required maintenance procedures. Upon completion of the maintenance procedures, the removal sequence was reversed for reattachment of the pylon to the wing. During the reinstallation process, following installation of the forward attachment fittings, the NTSB believed that manipulations of the forklift caused the pylon assembly to rotate, allowing contact between the upper portion of the aft bulkhead and the wing clevis. On a subsequent flight, the loads transmitted into the aft bulkhead caused the crack to grow, resulting in a fracture of the aft bulkhead. The fracture of the aft bulkhead allowed the engine to rotate up and over the left wing, initiating the accident events.
Now let's take a quick look at the FAA's final report. So the flight crew reacted to the engine separation as if it were an engine failure, and they followed procedures consistent with that type of event. We've already discussed that. The National Transportation Safety Board determined that the probable cause of the accident was the asymmetrical stall and ensuing roll following the uncommanded retraction of the left wing outboard leading edge slats. Now remember, we discussed this in one of my other videos, that when there's an accident investigation by the NTSB, they invite parties to help with the investigation. Now, they don't have to invite anyone except for the FAA. The FAA can become a party if they want to, and they should, and they usually are. So the FAA is the only one that they cannot exclude, so they can't ask them not to be a party. So just keep that in mind. So the FAA is getting all the same information that the NTSB is getting. So there were severed hydraulic lines causing a hydraulic loss of pressure. This is what caused the slats to retract. They had electrical power, and that resulted in a loss of many aircraft systems and instruments, including the captain's flight instruments, the left stall warning computer, the stick shaker, which is a stall warning motor on the number 1 engine instruments, the slat disagree warning system, and parts of the flight control indicating system. So they did what they needed to do for what they thought was happening. Pretty much most of the things are the same in this or the other. The service bulletin instructions assume that the engine and pylons removed separately and did not provide instructions to remove the engine and pylon as a unit. Removal of engine and pylons as a unit was not an approved maintenance manual procedure. So we've talked about it. The maintenance manual procedure is remove the engine, remove the pylon separately. So that's how you do it per the maintenance manual, and that's what McDonnell Douglas suggested. American Airlines said, that's going to take us too long. We're going to do it a different way. And the whole reason behind that was to facilitate time. Time is money, so they want to save as much time as they can. Now, using the forklift, the FAA also points out that there was a lack of precision associated with the use of the forklift. You're talking, they're talking 0.001 inches, and I just don't see how you can perceive that when you have somebody driving the forklift making the adjustments and somebody giving you hand signals as to what the adjustments should be. Now, I told you the last video I found a discrepancy in both the reports for the NTSB and the FAA. And you've already seen it in the animations that have been provided. Both the one from the History Channel, which they got their information, it appears directly from the NTSB's report, and the FAA's animation, which they made themselves. So here is a clip just showing the two differences so that you can see, and then I will show you what it says in the reports. So let's go ahead and watch these two back to back, see if you can catch the differences.
During the reinstallation process, following installation of the forward attachment fittings, the NTSB believed that manipulations of the forklift caused the pylon assembly to rotate, allowing contact between the upper portion of the aft bulkhead and the wing clevis.
After a forklift was positioned under the engine, maintenance personnel disconnected the rear attachment point of the engine pylon assembly. But before they could remove the front attachment bolts, the work shift changed.
And while they were gone, the hydraulic pressure in the forklift had a leak in it or changed, and it tilted the pylon, which they didn't see.
This caused the rear attachment point of the engine pylon assembly to jam back up into its fitting on the wing, cracking the rear bulkhead of the pylon. The new work shift didn't notice the damage, which occurred inside the pylon, and finished what they thought was a routine repair.
Now let's go back and take a look at what the FAA's final report said. And it's just a very small excerpt here. It says, during reinstallation of the engine pylon assembly, replacement of the forward pylon wing fitting bolt prior to replacement of the aft fitting allowed the engine pylon assembly to pivot around the forward pylon bulkhead fitting during reinstallation. Now let's go and look at what the NTSB says. This is what the NTSB says, and this is what mechanics told him what happened. So mechanics and the inspector who performed the spherical bearing modification on the accident aircraft recounted the operation for the safety board. The midnight shift started the modification, removed the aft spherical bearings, bolt, and bushing before going off duty. So they removed the thing that was supposed to be removed last first, and then they left their shift. When the day shift reported for duty, two of the mechanics saw the upper lug of the aft bulkhead come in contact with the bolts attaching the clevis to the wing. These bolts are located at the top of the clevis. The forklift's engine was running at the time, and the pressure gauge reading was 18,000 pounds. When the crew could not remove the forward attach assemblies, they discovered that the engine stand was misaligned. The clamps holding the cradle to the stand were loosened, and the lifting forks and engine stand were shifted to the left forward on the engine until the cradle was properly aligned on the stand. The clamps were then affixed, so with the weight of the engine only on the forward mount, they loosened the clamps so that they could move the engine stand. That doesn't sound like a very safe practice to me. So according to one mechanic, the stand was moved forward about 12 inches. After the stand was realigned, the forward, upper, and lower attach assemblies were removed, and the engine and pylon assembly was lowered to the hangar floor. When I'm reading this, it doesn't seem like a whole lot of things went right during this. But let's go on further down and we'll find out exactly. This is how they recounted it. So let's see what the FAA says, or the NTSB says happened. So item 15 of their conclusion is American Airlines personnel removed the aft bulkhead's bolt and bushing before removing the forward bulkhead attach fitting. This permitted the forward bulkhead to act as a pivot. Any advertent or inadvertent loss of forklift support to the engine and pylon assembly would produce an upward movement at the aft bulkhead's upper flange and bring it into contact with the wing clevis. So from this statement and the previous statement, The NTSB found that this happened during removal of the pylon and engine, and the FAA found, and they improperly stated in their animation that the NTSB believed, but the FAA found that it happened on reinstallation. So it's the difference between install and uninstall. But I think it's a key difference, and I'll show you why. So when you're inspecting something, access is everything. The greater the access, the better inspection you're going to be able to have. So when you look at these next two little clips, you're going to see if it happened on removal, if they removed the engine and pylon and then moved it out from under the wing, then they have a lot of access around this attach point that they can inspect. And remember, the damage only happened 1.5 inches to an inch from where the repair they were actually doing was. Now, if they didn't do this damage until it was installed, then you see from the other video, you have very limited access, so it's going to be much more difficult to see the damage. So if it happened on removal, like the NTSB says, then they didn't address an issue that I think they should have been addressed, and that is inspection procedures. Because you need to inspect what you're doing, and you have to look around what you're doing. And actually, the service bulletin says inspect the bulkhead. So if they took it down and they moved it forward and they could actually see it and see the bulkhead and there was damage already there, they should have noticed it. So that's why I think this is very important. So playing Monday morning quarterback is easy. Now, I said in my first video that I was just going to report, I'm just offering the truth or the facts as I see them. The facts as I see them is there is a discrepancy between the two reports. If you think that discrepancy is important, leave a comment. If you don't think it's important, leave a comment. I'd like to know what your thoughts are. Now, my next video is going to be on how this was allowed to happen, what things are in place that lets this happen. So stay tuned for the next video, and thanks for watching. Peace out.
Eventually, 6 other DC-10s, 4 with American Airlines and 2 with Continental, were found to have pylon cracks caused by the faulty maintenance procedures.